Welcome to the first lecture on robotic mapping. In the next two lectures, we will talk about building a map, a representation of the robot surrounding based on relative noisy observations that we obtain using onboard sensors. So the first idea, which is the most common way of building maps on many robots in 2D environment or 3D environments when the robot is moving on an even floor, that we can assume the map, the layout is 2D, and that's enough for the robot to move from one point to another. It's called occupancy grid mapping. And it is a good way to introduce you to this area of the mapping. Next time we will talk about 3D, the extension of it, some of the ideas that will basically fix some of the problems that we raise for this basic method today. We will also show you that there are open source libraries that you can use at this point that can address a lot of projects that you might work on without building on it. But the research is ongoing, and this is an open area of research in robotics. The first thing we need to talk about is the idea of the map. How do you define a map? How do you represent a map? How do you visualize a map? There is no unique way to do that. So that is a fundamental problem, because if there is no unique way to do that, then we can come up with several ideas, many ideas, and depending on the application, some of those ideas might be shown to be better or more efficient. But depending on the computational resources we have, we might opt for a particular representation. So that leads to multiplicity of ideas for mapping and how to show the map. For example, in this figure, on the right, you see a data set called Victoria Park data set. This is a famous data set. It was collected in late 90s or early 2000 in Sydney. And that's where I used to go to school. That's where I did my PhD. I used to swim in this pool. And there's a shopping center here. I used to do my groceries there. So this is a very important data set to a lot of people. But the landmarks you see are these points. Now, what are these points? This is open source. There was a truck, like a utility vehicle. They moved around the park and collected the data using rangefinder sensors and odometry for wheel movement of the car. So the landmarks, the points that you see, these are obtained after processing raw sensor data from a laser rangefinder, a 2D point cloud, to detect the trunks of the trees in the park. So the entire tree, when you detect the cross-section of it, which is the height of the vehicle, not very high, it will probably give you some line if you look at it from the front view, but you can consider that as a point. So there is a part that processes that data and will give you these 2D landmarks. It is open source. It's a piece of MATLAB code. It will process it for you. And that's one way to represent a map, because now we know that if we fix the coordinates somewhere, and then if we knew the location of every landmark, let's say XL and YL, if we move and we can detect these landmarks, we can localize using some of the ideas we learned. Maybe an extended Kalman filter, maybe a particle filter. We can solve the problem. And this is one way to represent the environment. Now, the challenge is, of course, that in this case, we don't know the locations of these landmarks. So the research is on SLAM, simultaneous localization and mapping. Not only we want to recover the trajectory localized, but also we want to estimate the location of these landmarks, because we only know them relative to the sensor frame at each time step as the vehicle navigated the environment. So this is a SLAM problem, but if you know the landmarks, this is one way to represent the map, and we can use it for localization. Now, another idea that today we work with it is representing the environment in a way that you could call it dense. That means for every part of the environment, I am modeling some, here, a probability. A probability if that particular grid or point is occupied or not. That's another way. Maybe it's 3D. Maybe we want to reconstruct and show the objects the way they are. That's also a representation. But you can imagine that this 3D is, of course, much more intensive computationally than something like a 2D map. So volumetric map versus feature maps are one way. Or you can talk about mesh. A lot of research in computer graphics is about how to model objects and show them. Some of them are really good. Some of them are not directly transferable because they are, again, intensive in terms of computation for onboard computation. So that's one problem, and today we're going to talk about this type of mapping, and I'll tell you why we might need a map like this for navigation as opposed to landmarks. That does not mean that we cannot use both of them at the same time, but there are benefits in the dense reconstruction that we are not getting from just tracking points. So the grid maps idea is that to discretize the world into cells. So this grid structure will be rigid. That means it's a piece of map, grid, in your memory, and it's rigid, it's not going to change. What we're doing, we're just updating the belief, the posterior, the probability of occupancy based on observation we receive, and we want to update it recursively, of course, because we see a chunk of the environment, and then we move, we see another piece, we want to recursively update the map. Now, the fundamental assumption that we will go over it is that these grids are independent, statistically independent from their neighbors. And that is the fundamental assumption to this type of mapping. So each grid is assumed to be either occupied or free. So we only talk about the occupancy. If it's occupied, that means if you hit it, this is an obstacle, and you might not want to do that if the goal is to do obstacle avoidance and navigation. If it's free, what does it tell us? We'll get to this soon. Here is an example of an occupancy grid map. This is a building in Freiburg campus in Germany. Again, the data set is open source and is available. You see, when you build the map, the black cells, the color map is usually grayscale from 0 to 1. So the darker cells means occupied, and brighter means free. When it's gray, it's in between range that we don't know, it's unknown. Now you can flip the color map, or you can choose different color maps, but this is very standard in papers and literature. So as you can see, when you zoom in, once you build a map, because the grid structure is rigid and resolution is fixed, there's no way you can increase this resolution. You're bound to this particular grid size. You used your data, the map inference is done, and you cannot increase or enhance the resolution. So this is built in, it's baked into the algorithm. Can be a problem or maybe not. You can still accomplish a lot of autonomy tasks using this map. But it is insufficient for general 3D scene understanding and tasks for today's applications that we have in mind. Now, the notion of free space is important if you want to plan. If you have a set of landmarks in the environment, and if you want to move autonomously in the environment, how does a robot know if a particular space is available for navigation or not? Just because we don't observe that area doesn't mean it's safe to navigate. That is somewhat obvious. So it is important to know where we can go, where we hit an obstacle, and where we don't know yet. So the occluded area or the areas we have not explored yet are unknown. They can be free or they can be occupied. But the robot knows that if you want to go from point A to B, maybe you plan a path like this. So the planner, you can use something like AS star or RRT star. It will find a path that the robot can navigate over all available cells, free cells for navigation, given previous data. So that's the importance of free space. Now, what if somebody is moving in the map? Or at the time that we mapped the environment, maybe it was empty, maybe now it's not, when the robot is navigating. And that's very important. The environment can be dynamic and not necessarily static. For example, maybe this is a museum. We have an example of a museum later. Maybe you map the building when it's empty, so that you save the map, the robot can navigate at a future time. But when we visit, maybe there are a group of people visiting the museum. And it's not as easy as moving A to B freely. So this map, as is not capable of modeling dynamic environment. So there is also an assumption that we will see that the environment is static. So the world is static. And then we infer this map. This is a built-in assumption to this method. If you only use odometry to build a map, you might end up with something like this figure. So if we are not solving SLAM, that means we're not simultaneously solving the localization problem, but we're going to assume we have access to robot poses from somewhere. And the problem is, in reality, of course, you don't know the ground truth. Ultimately, you want to get it from a source that might solve the problem for you from some measurements. If you get it from odometry, because the odometry comes with drift, you might end up with a map that is inconsistent. So the inconsistency in map refers to when maybe you have walls from multiple scans that are not being aligned well. As a result, what you see in the reconstruction does not match what we see, the reality, the structure that we see around us. And that is a problem. if you have a good SLAM algorithm, maybe it solves the localization problem for you. And if the localization is accurate, then you can build a map that looks clean, like this part. So besides the environment being dynamic, there are also other motivations for building maps. So a lot of times, even though we have prior information about the layout of a building, if it's an indoor mapping problem, it's probably good to know the structure, but the setup of an environment can change over time. For example, the CAD model might have this layout of furniture that you can see here. But at a later time, the setup can change. Or the environment itself, it can have small changes. So the ability that we can send a robot and reconstruct the scene as is, and do it fast, as frequent as we want, is very useful. Because then we don't have to manually maintain and update the maps to feed it to maybe a robot to navigate. So just like localization, this is a very fundamental problem in autonomous robots. Something that is more real world, for example, a self-driving car. There are high definition maps. The car can use it to localize and move as they do. However, maybe because of some accidents or road work, the road network that we assume we know is not the same. What about that? Now suddenly maybe we have to navigate on the opposite side because that's just how it is. There's an accident, maybe the cars are taking turns to move along from each side. And these are not things that we can hard code into the robot that will happen at a particular time. These are unexpected events that requires online scene understanding and mapping. Now that is a much harder problem because we also need to understand some signals. Maybe a police officer is telling the cars to come now, and then the other side, the autonomous vehicles will not understand that. So that's a much harder situation. And this is maybe a more manageable version of that. We want to just model the occupancy, not that we understand the intention of people around and reading different signals that we see in the environment. Because the light can be red, but the officer is telling you to go. And you need to get a resolution for that. It's easy for us. And it turns out it is extremely difficult for a computer vision algorithm to understand it. So there are many motivations to have this capability for the robot, to build online maps and understand the scene. So we navigate in the environment, and we collect some scans using a rangefinder sensor. A rangefinder sensor will shoot infrared beams with some resolution of the beams on the sensor. If it's 2D, it's like this. And some maximum range, and it will return the distance to an obstacle to the sensor. It measures the time of flight of the infrared light. We know the speed of the light, and then we know the distance. Now, when people moving around, you see all these outliers and dots that it's true that there were obstacles, but they're not a static part of the environment. We don't want that in the map because they will leave artifacts in the map. What we want to do is that to come up with a probabilistic method that ideally can give us this clean map. So we want a certain level of robustness to outliers and moving objects, if it's mild. So we can still reconstruct these static things. Hence, this probabilistic idea of inferring a map makes sense because we deal with some level of uncertainty in what we observe. Observations are not absolute and deterministic.
Can you direct post-processing image processing during outlier?
So the question is, can we do post-processing to remove the outliers? Yes, but we want to build the map as we see. If you have the option to process data offline, we can build something like HD maps, high-definition maps for the cars. So we can do a lot. But if we want to build the map on the fly as we operate, you have a very limited time window to process that data. But yes, maybe you build the map and then you look back at the history with some software engineering. Maybe you have a parallel thread to look through some other parts of the map and update them based on some other ideas. So it's possible to come up with clever ideas. Today, we're going to talk about a very basic introduction, how to build this map online. So the occupancy grid mapping idea was introduced in mid-80s by Moravec and Elfas.
So I was just curious, just because we're talking about LiDAR, is it reliable in like different environments, like rain, for example, or is it like, yeah, hey, that's my question.
The question is, what happens if it rains?
Yeah, or like snow or dust or something.
Nothing happens if we're inside. So that's what we know. If you're outside, well, that's a problem. Just like cars moving around, people moving around, that's a problem we have to deal with. Yeah. So we're not zooming in too much in these particular challenges, but all of these make the problem only harder because you fix one or two of them, that's already hard, and then there are 10 or 20 of them left to deal with. And that's, again, what makes this area so wide open with so many ideas, so many people working on robotics mapping. Now, one question that is relevant to today's research is that some people actually say that, well, why do you need the map? Why not just go for a mapless navigation? You can do end-to-end mapping. So there's a famous paper by Professor Kuipers here in Michigan. It's called The Map in the Head. How do we store the map? Are we seeing the map or are we seeing images? Now, if you refer to yourself what your eyes are seeing, it looks a lot like images. Now, I do not know with certainty, but it's more relatable as if it's a camera that is seeing the scene. What is the representation that we have? Whatever it is, it's pretty good. We can accomplish a lot of tasks. So it's a compelling idea. Maybe there is no need for explicit representation, and maybe there is an abstract space that can capture everything. Now, the problem with that is that the black box mapping for a robot might be doable, but it will not make the method explainable or interpretable if a robot wants to interact with humans. Imagine a team of rescuers are going into the fire somewhere in the forest to help people. Imagine a team of robots also collaborating. How are they supposed to exchange information and collaborate if there's nothing to share? They can just talk about the end results. So it might be beneficial for the human team to have access to the areas that are explored by the robot by knowing and seeing in some way what happened and what was mapped. So there are values to it. So again, just like a lot of ideas, it's not that one is correct and the other one is wrong. There are certain applications that you might want to have an interpretable map. Probably there are applications that maybe you don't care. Maybe if you try and maybe if you accomplish the mapless navigation, that will work. So back to this invention in mid-90s, they used noisy sonar information, acoustic signals. At the time, there was not a laser rangefinder, or if there was, probably it wasn't something that they had access to in robotics labs. Because we see laser, a lot of people think that's a mass destruction weapon, but it's like a remote control laser. That's why sometimes there are export limitations and constraints on these sensors, because the thing is laser. You're going to cut people with a robot. It's more like a remote control. So they had noisy sonar. So acoustic signals, obviously, the acoustic travels in a cone, and it's very rough. It's not sharp like laser to return a point. It's a rough measurement of an area that maybe returns a point, but it corresponds to that area being occupied or not. So they called it mapping with known poses. So you know the robot pose, and then you try to build a map. The question was how to do it, and their idea was to, let's do this probabilistic reasoning to incrementally update the map. So in 1987, we had occupancy grid maps. And I think they were working with the stereo cameras in NASA JPL. Also, there was a time that they were also talking about visual odometry, occupancy mapping. So I was not with them. I was born in 1987. But you can read some history. So it wasn't solved because part of my PhD was on occupancy grid mapping, even though I was born in 1987. So I used Gaussian processes to build the same map. That's a regression way of doing it. It's not discrete anymore. Now it's continuous. You can get variance. You get a whole distribution over the environment. It captures the correlation that you have between different points in the environment. If this is a table and there is a point here that you observe and it's occupied, there's a really good chance the nearby points are also occupied. So that structural correlation can help you to have better inference, more accurate inference, even though the point cloud observations from the sensor are still sparse and noisy. So a better model can give you better results. But the cost of that Gaussian processes was that the method was that it is cubic. To run the inference, you can come up with some simplification, but in its native form, you have to pay the cubic computational complexity because you have to invert a matrix that is large for the training data. So next time, we will make this continuous, but with a new method that it is from the family of kernel methods, just like Gaussian processes, but it's an approximation to Gaussian processes. It reduces the inference time to log n instead of cubic. So that's what we're going to talk about next time to make the map continuous, and 3D, and semantic. So no room for If you want to do a work, finish it. Don't leave a room. No, I'm not serious. There's still a lot to do because you add all these good features and you say, well, this is it. This is the end. But then you run it, you see, there are still a lot of problems. So it's still, even though it's continuous, you need to somehow represent it in a way, right? Now, Arthur played with the grid map a little bit. You model the ground, and the voxels are 3D grids, are still up and down. You see, it's like Minecraft. It's not flat, and I mean, we know it's navigatable, and then the robot moves there. But if somebody gives that to you, and it looks like off-road, even though it's a road. So still a lot to do. But it's progress. Now, imagine you have an area that is 25 by 25 meters. You need to pick a resolution for the grid. What resolution you would pick? Clearly here we pick 25 centimeters, but it depends. Is 1 meter grid size good for navigating inside a building? Probably that's a bit too coarse. If you pick 1 centimeter, then maybe that's too fine, and you need a lot of memory and calculation. So there's a trade-off. Based on your application, if you use this method, you probably want to tune a resolution that makes solving the problem feasible while you can use it. So if you have 25 by 25 meters area, and the resolution is 25 centimeters, then you're going to have a 100 by 100 grid, and that will give you 10,000 cells. That's already a lot of variables. In a localization that you do for the Kalman filter, in 2D, you have 3 state variables, x, y, and heading. Right now, this is also a state estimation problem. We want to infer the map instead of the pose. Now, currently, the state is 100,000 or 10,000 here. And it's not that big. This is 25 by 25. This is a relatively small area. So clearly, a naive attempt to run an off-the-shelf inference might not work, because then you have to handle a lot of data. You can't just run a method like Gaussian processes that handles everything in batch, tries to infer something for you. So that's what makes this idea good. We can handle sizes like this. But let's say we consider the state not to be a continuous value, to be a binary value. 1 if it's occupied, 0 if it's free. How many possible maps we have for this probabilistic state? So we have 10,000 cells. Each cell has 2 possible states. So you get 2 to the power of 10,000, something like this. But it says something else here. This was an old joke. I had to unlock it. This is not my slide. Now, this is binary. This 10 here is 2 in binary. If you evaluate this, it will tell you roughly 2 to the power of, or it'll give you something like this, but I think this is binary. Yeah? the question is, do we consider the map to be the configuration space, just like we did for localization? No, not in that sense, but it still is part of the state that we want to estimate. And if it's a dense reconstruction, now regardless of the specific value here, there's a lot of variables. This is just a small example to show that it grows exponentially. You go to 3D, this grows even so much faster. So we don't form a state to build a traditional state estimator like a Kalman filter or particle filter, although you can do such a thing for each grid if you want to individually, but never jointly.
So EECS has just the position, not the.
It is ultimately like a landmark is a position. That's right. So there are ideas to run tiny EKFs or particle filter to estimate some quantities for each cell. People do that. But and you can consider a neighborhood if you want, but it's rare. It's never for the entire map, because that's just not tractable. So what is the idea for inference? That's what we want to learn today. So the assumption one, so it's good always to list your assumptions when you're developing an algorithm. It makes it easy for other people to attack it. Maybe not something that you like to hear, but that's how we can make progress. Other people can come and maybe relax the assumption or change it to a milder assumption. Because if you make enough strong assumptions, usually you can solve anything. And then the goal is if you can relax the assumptions and make the problem more realistic, eventually we will have something that has utility in real life. So the first assumption is that a cell is either occupied or free. So the state is, in some sense, binary. So that leads to the representation of the environment that is telling us if a cell is cell I, the probability of cell Mi being 1 implies that it is occupied, and the probability of this cell to be, the probability being 0 implies that it's free. That's how we model it. You could choose the other way around, but this is how we model it. So 1 is the probability of being occupied. 0 being free, no knowledge, something in between, 0.5. That's the prior. Now the world is static. We do not assume that we are dealing with dynamic objects, although when we operate and build the map, it can happen and we might come up with some better maybe models to handle them in some part of the algorithm that we actually implement. So if it's static means that if it's inferred that to be occupied, it's always going to be occupied. It won't change its status. It's not changing over time. We will see that in the graphical model that will come up in a bit. Now, a fundamental assumption is that the cells are independent, meaning when we perform inference for a cell, we only look at that cell. We don't look at the neighborhood. And the immediate thought is that it sounds like a good idea to look at the neighborhood. Yes, but that will make your inference more complicated, which is the next generation of this algorithm. But today, we learned the core idea that is independent grid assumption, which makes it super fast. Then you can implement it and run it on a very weak computer. You can run this mapping algorithm. So as a consequence of assuming that each cell is independent, mathematically, your posterior over map, so the map is maybe a list or tuple of whatever number of grids we have or cells we have. It's a list of all of them. All together, that's the map, not just one cell. And the consequence of the cells being independent, that means the probability for the entire map is just the product of individual probabilities. They are statistically independent. That's the assumption. Okay?
So my question is, the mapping that we discussed has three assumptions. And so my question is, right, so you're kind of saying that more test algorithms, break these assumptions. So my question is, do each of these assumptions have like different weights? Meaning, if breaking this particular assumption will give you the best trade-off to between computational complexity and accuracy improvements and things like that?
The question is that do we know particular weight that the outcome will get influenced by if we relax or break these assumptions? We don't have an exact table that says if you break this, you will get 10% off on the accuracy. We don't have that, but if you mean that how that will affect the computational complexity and performance, that's the case by case, depending on how you do it. Because even though you might subscribe to the same assumption, maybe you choose a different approach for modeling. And that can lead to better performance sometimes. So that leads to research work that case by case people have to study. And it is always good if you have an algorithm to talk about its computational complexity. You can tell people it's polynomial time, but is it to the power of 8 or is quadratic? Quadratic is already not very scalable. If you're running a Kalman filter, extended Kalman filter SLAM, and now you have 1 million landmarks, that's not going to be scalable. If you have 100, 1,000, I think it's doable.
What does P of M represent? I understand the algebra, but what is the distribution over the entire map?
So another question is, so to end that question, it's the research problem case by case. Next time we'll talk about, I'll point out the complexity of this algorithm when we see the method. So another question is, what is the distribution of the map? We don't know. The true distribution is something we don't know. The way we model it, we break down this posterior that we don't know what distribution it has. It's complicated because it needs to model this room, for example. It's not going to be a nice Gaussian. At the very least, you can assume this is a mixture of a lot of Gaussian terms. If everything was smooth and boundaries weren't sharp, it would be like that. So we don't know. We break it down to the product of many independent and simpler probability distributions. Now, we know these individual terms. And the way we model it as a binary distribution. Now, the question is good because if you give it an explicit distribution, maybe we work with that particular formula to have a derivation. And that's what we're going to do next time. Because although this is binary, we're going to take a direct approach and work with just probabilities. So that's like directly multiplying probabilities, just like what you did in Markov localization. So that direct calculation has a drawback that it's hard to infer the whole distribution. Because if I infer the parameters of a distribution, maybe I can talk about mean, variance, and higher order moments. So next time we will look into beta distribution, or Bernoulli distribution, or categorical distribution. Distributions that are explicitly, they have a model and we can work with them. So for now, think about this as just a probability between 0 and 1. We're not going to dive into a particular model. Does that answer your question? So very complicated. We don't know this. The goal is to have an approximation of this distribution. Which is a visualization of that answer here. If the map contains 4 cells and they are supposed to be jointly somehow distributed, we break it into 4 individual cells, and we just talk about probability of each cell. Now the joint, assuming they are statistically independent from the law of probability, that tells us the joint is the product of the marginals. That's why the right-hand side is going to be P1 multiplied by P2 multiplied by P3 multiplied by P4. And you already immediately, you probably want to say that, well, you're going to be in trouble if you keep multiplying these probabilities. If one of them is almost 0, we're out of numerical resolution to track that number. So we want to come up with an idea to avoid keep multiplying these probabilities that can be very small, because that will make it impossible to implement numerically. So that's part of the discussion today. Do you want to take a break? Not tired? I want to dive into derivations of a binary Bayes filter. I told you, you said no. All right, so now let's make it more realistic. Well, the problem is that we want to infer a distribution of the map M given measurements and robot poses. On top of that, we assume that we're going to just break down the posterior into the product of the marginals. So we want to talk about how can we infer the probability of one individual cell if I know, let's say, scan a 2D range measurement, and I know where the robot is. So I want to infer that probability in a global map that I'm tracking. And I want to update it recursively if I'm observing that again next time. So that leads to a filter that it's called binary Bayes filter, because it's in that framework of Bayes filter, but because the map, the state now is binary. In Kalman filter, it was a Gaussian distribution. In particle filter, it was a set of weights, like a histogram, an empirical distribution. Here, it's binary. It is simpler. That's called static binary Bayes filter. So the graphical model is like this. The robot is at time t-1 here. Then we move to another pose, and then we move to another pose. At any time, because we are at this particular location xt, we are going to observe measurement zt. And the measurement is caused by the robot being there and the fact that the map has a particular shape. So the arrows are showing that what is causing what. So the measurement is caused by the robot being there and the fact that the map has a particular shape, which gives us that particular laser scan, range measurements. Now, this is typically standard to color the nodes. The gray means we know them. We're not going to try to find values of x and z. We know them. M, the white node here, is the unknown. We want to figure out what's the value. Now, the reason the map is not moving to different states, because it's static. If it was dynamic, then it needs to evolve over time. So you can see that it will be much more complicated because you get one shot to see that area. When you move, it can change, and you might not see it. Later, next time you see it, it's changed. It's not what you have in your prior. How are you going to rectify this inconsistency in what you observed before, and that's your belief, and what you re-observe, and they don't match? So that's the problem with dynamic mapping. I point out in the end of maybe next lecture some references that you can look into for dynamic mapping in Islam. So let's start from, where should we start?
So, question about the previous slide. So, in this case, right, like typically, so x corresponds to basically a robot position, right, and z corresponds to whatever sensor data is collecting. So, isn't x also going to be something that you're calculating rather than being known?
The question is, are we going to calculate x? No, x is given. It is known. We know its value completely. So that's why we say here, robot positions and orientations are given. We know them. So anything on the right-hand side of this midline in the posterior is given. If it was a slam, meaning that we want to solve for pose and the map, I would write it like this. Posterior like this means that I want to solve for the map and the robot trajectory using only relative measurements. That's the slam problem. Localization is, so this is slam, this is mapping. Localization is what? Given a map and a measurement, find the robot position. So if you do it jointly, simultaneously, then we have to estimate both. Which makes it difficult because if you get an incorrect estimate of any of them, it can affect the other one. So we don't have many places to start. We only know Bayes' rule. We have the total law of probability, marginalization rule, that we use for prediction. There's another rule for taking expectation or prediction, but that's about it. So let's start from Bayes' rule, because that will connect us to the prior as well. So the Bayes' rule, if you remember, of M Z X will be probability of Z given M and X, some prior So this would be the Bayes rule if I just use the static parameters. But we have this time sequence that, if you remember, that's the notation we established, that z1 to t, this is actually a lot of variables from 1 all the way to t. So when I write probability of z1 to t, we're talking about the joint distribution of z1 to zt. So I can always separate one of them and then write the Bayes rule by keeping this particular measurement to be here. So that's what we're doing here. Now the reason we do that, because we are after a recursive process. So it is in our best interest to keep the latest measurement we get and then try to come up with derivations that the posterior from previous time will pop up at some point, and then we recognize it. Then starting from a prior, we can just recursively update the map. So that's why we write it like this. So we write down the Bayes rule, and we apply our familiar Markov assumptions. If I know the knowledge of the present time, right, then I don't need the history. So I can drop the measurements and only keep the latest robot pose, xt. But also, I don't need future time in the prior. I can drop the information from future to be in my prior. That's how we're going to model it. Now, the problem is that a likelihood like this for something like a map is very difficult to model. Because if you remember for localization, the likelihood is such that it assigns a likelihood, a value, to a measurement given some hypothesis for the state variable. For example, for particle filter, given each particle is somewhere, take that as if it was true as a hypothesis. Then evaluate the Gaussian distribution based on the measurement you get. See what you get. If the value is very peaked, that's very likely. It matches the model, what you see from the sensor. Now that was relatively easy to evaluate, but what about the map? There are just so many variables and so many possibilities. So it's very challenging to work with this, and you may call this forward model because the forward way of just driving it, it leads to this model. So the idea that you read in the probabilistic robotics book is to write down the Bayes rule again for this part, to flip the likelihood to give you something like this model. Now we call this inverse model because now instead of z being conditioned on m and x, m is conditioned on z and x. It looks like the posterior, however, it is only conditioned on the observation at time z and the latest pose. So that's the difference. There's no need to talk about the entire history, only at time t. Then we're going to get another prior and some denominator for normalization. So we're going to substitute this inverse model instead of this term forward model here. So once we substitute it into the equation, we get something that is a little more complicated. And there are some extra terms that are hard to compute. We don't know yet what to do with them. Fortunately, the map is binary. So we're going to do a trick in the next slide. The final simplification is that for the denominator, when I have P of mi conditioned on the robot poles, for convenience, we're going to drop the conditioning to make it the marginal probability of the map. Now, this is not true because where the robot is located right now, obviously, is free. But we're going to give up on that one cell information. We're not going to use that information to update the map. So if we give up on that, that makes the math considerably simpler. So we end up with a prior over the cell. Now, the trick is that because it's a binary variable, you can write down the exact same equation and derivations by just negating the map variable. And when you do that, you get the right-hand side, looks like what you had, but m is negated. There are terms that are hard to compute. How about we divide these two guys to get rid of them? If you divide them, you can get rid of these terms that we have no idea how to model them. So we got rid of difficult to calculate terms. What's left is what you see here. Because the map is binary, the negated version of cell I is 1 minus probability of being occupied, right? So the probability of negative of m is basically the cell being free instead of being occupied. You have a question, Ezra?
Yeah. So the robot is occupying more than one cell, right? So
We don't know that. You're saying that a robot occupies more than one cell. Maybe, yeah. Depends on the resolution of the map and the robot size.
I suppose, right?
Yeah.
Well, so is this making the assumption that the robot does occupy only one cell, based on what you were saying before?
That's what I said, but if it's more, we still give up on that. For small robots, it's usually 1 or 2 cells. But yeah, that's a good point, because if it's a car, that's a lot more than one cell. Do we want to give up on that information? Maybe you start somewhere and then you see what's in front of you. Then from there you keep going and you don't never have a problem. So.
Or it could be a small robot, but also a small map that it's dealing with, right?
Yeah, if it's a small map, a small robot is fine. If it's like a car on a road or some way of moving that, when you see what's ahead of you in the future, that's never a problem, because as you move, you already see what's ahead of you. You never need to update where you stand. It might be okay. For a static world, it is okay. Now, there's a deeper problem, right? There's a certain question of awareness that the robot is aware of where it is, which is not. But it's not important, because ultimately all of these are correlation-based inference. These models are not slightly conscious. There was some debate on Twitter. Some neural networks are slightly conscious. What do you think? I am interested in your opinions. One of the only times. I'm waiting.
Don't they use neural networks for topological stuff, neural networks to show neural network that might mimic cancer. So maybe that has.
Okay, your master idea is that let's look at the topological structure of a neural network and look in the number of holes in the network, figure out if it's conscious or not. That is very abstract, maybe. It's a good question. Now, a lot of people don't think it is because neural network is modeling a correlation between input and output. It doesn't understand causality. We don't know what caused what. We just know the correlation to map the output to the closest interpolation and extrapolation of the input.
You could argue that people are doing that to some much more complex level.
Then you argue that the networks are getting more and more complicated. If you claim that's the Bertrand-Russell argument, if you claim there's a teapot in the space rotating around the moon or Earth, but it's so small that nobody can see, it is on you to prove it. It's not on me to disprove it. But that's the goal. I mean, if we can one day we can have consciousness for the robot, that's exciting and scary at the same time. So I don't personally think that the consciousness is all algorithmic. There's a lot of it is embodied, is biological. There isn't any conscious mind in nature in vacuum because we don't have that. All the conscious form of life, they are embodied in some ways, right? Whether it's a bacteria. They're not conscious. Humans are conscious. So if we're the example, we have not seen yet an example of, what's the term, unembodied? Consciousness. So that's...
You can take the Turing test.
Hmm?
You can take the Turing test.
You can make them take the Turing test.
We also only know behavioral consciousness. We can't actually detect consciousness.
Well, if you get a robocall, you might believe that's a human at some point. That doesn't mean the robot behind the call is conscious. Or maybe it slightly is. We don't know. But it's pretty cool. It's a cool topic to think about it. So it's not all about occupancy mapping. You can spend some of your time to read about these futuristic and sci-fi ideas too. We are interested in these ideas in robotics. If we don't teach it here, because we don't know how to do it. That's the only reason. We're covering occupancy grid mapping today. All right, so now we got the recursive terms. The first part looks to be only using the observation at time z. Now there is a recursive part that we wanted to see this whole term here. This is the posterior at t minus 1, because when you compare it to this term, it is the posterior, just at the previous time step. So that's what we wanted. We have a prior term, which is good. We need to start somewhere. And we know how to start. There's a probability of 0.5. We don't know anything. That's the prior. So get the prior, the ratio, not the probability itself, multiplied by the previous ratio of the posterior divided by 1 minus the posterior, then multiplied by whatever is the evidence, the likelihood from data at that time. Then you can recursively update the posterior. However, this is not compelling to work with because we are just multiplying probabilities again and again. We end up with numerical problems in a computer. So to find something that is more compelling, we're going to work with log odds. So this ratio of probabilities is called odds. If you've done gambling, you should know that. Say the odd is 3 to 1.
On the last slide, can't you end up dividing by 0 on that expression?
We might. Yeah, that's also a good point. So generally, there are a lot of problems here, because if the probability is 0, now we're not going to pick a prior that's 0, because you're intentionally breaking down the algorithm from iteration 1. But you're right. What if we do have 0 at some point? Because at the end of the day, we're modeling the probabilities to go to 1 and 0. It can happen. So it's not compelling to work with. There are a lot of numerical problems. The log odd will fix that, because then we're going to just add terms. So that's the reason you don't see this equation anywhere to be coded. You're going to end up with numerical problems. So the odd of not winning or versus losing, but being occupied for a cell versus not being occupied. And we take the log of that, because log will convert the product to sum. And we like that. We can add numbers instead of multiplying them. That will remove the risk of multiplying with a very small number. And because we only track maybe 15 or 32 floating point numbers, that will be a problem if you have small numbers. And it's also nice that you can always recover the probability from the log odd. It's just the inverse of that. A straightforward calculation will show that you will get this. This part might remind you the logistic regression model. Because the logistic model gets some function, and it will squash it into the interval between 0 and 1 to make it a probability. Its generalization is the softmax that you use in neural network for multi-class classification. So log odds, we talked about it. It's nice because it alleviates the problem of numerical issues. We can add terms and avoid truncation problems. Now the range of log is from minus infinity to positive infinity, and that's not a problem, because when you recover the probability, it will squash it. That logistic form will squash it between 0 and 1. So based on probability of 0, you have minus infinity, and 1, you have positive infinity. Now, if you choose something like 3, you're going to get already something like 1, right? You don't need to go to infinity. So you can see something between minus 3 and 3, minus 2 and 2 is the range that you might expect to see these log odds values until the probability is completely saturated. So if you take the log of both sides, we have this nice formula that the log odd of the posterior equals the log odd of the term that relates to the likelihood at time t, using that inverse sensor model idea, plus a recursive term from previous iteration of the algorithm, minus a prior. Because the other two are p over 1 minus p. The last one, the prior, is 1 minus p over p. So that's why there's a negative sign. Okay? So the log of what we're doing, we're saying that log of x, y, z is log of x plus log of y plus log of z. And that this last part needs a negative because to match the way we defined the log odd was the probability divided what minus probability, not the other way around. So we are done, except that we need to talk about this algorithm because we still don't know how to evaluate the inverse tensor model. Now before that, this is the algorithm that you might call occupancy grid mapping. You get to start with the previous belief in form of log odd, current position and orientation, and current measurement.
So if you find the prior map as L0, suggest that it's a constant?
Prior is constant, and you might define L0 to be log of 0.5, 1 minus 0.5, log of 1, which is 0. So it can actually disappear if your initial probability for a cell is 0.5. The log odd is 0. The probability is 0.5, but the log odd is 0. It's a prior. Now, maybe you start from a map that you built yesterday. It's not 0.5, it's something else. Then you can consider that as the initial, the prior per each cell. Does that make sense? So we're saying that if the cell M is in the perception field, now there are many ways you can implement this, but this is a simple way of thinking about it. For all the map cells, if the cell is inside the perceptual field, that means we are currently observing it. It's within the perceptual field. Update the belief probability using the log odd formula. Otherwise, don't do anything. Just leave it to be what it was. Now, the computational complexity of this algorithm is clearly linear in the number of cells in the map. Because of this for loop here, if you have, let's say, n number of cells, we have to loop over every cell. And we have to check if the cell is within the perception field or not. So a naive implementation, it will give it linear time complexity, assuming that this will take some constant time to evaluate. But probably you loop over all measurements, and maybe you have m beams for the laser, so it's like linear in the number of beams. But m can be much smaller than n, probably. So it's not too bad, and you can come up with ideas maybe to just search in a neighborhood in the map based on where you are. You don't have to loop over the entire map. Then it will make it much faster. That shows the importance of a data structure. A naive memory assignment for this type of problem is not very efficient. If you have a good data structure, that will allow you to search fast, query fast, and update fast. For 2D problems, for spatial problems, quad tree is a good data structure. For 3D, we will talk about octree that we use in 3D mapping. This is a data structure that will divide each map to 4 grids, and then you zoom in and divide it to 4 more grids if you need. Otherwise, you just leave it to be a giant block. So it's used a lot in different types of geo information processing, and it's useful here as well. The octree is the 3D version of that, when you have 8 neighborhood blocks to process. KD3 is the general version of this data structure. KD3 is not for physical spaces, it's spatial places. Quad3 and Octree are for 2D, 3D spaces that we have data. It's more efficient for this type of problems. But if you have a general data set, you probably want to look into KD3. So what is the inverse sensor model? If we know that, sounds like we can implement a version of this method. Now, suppose you have a rangefinder that it has multiple beams, but for the sake of visualization and conversation, let's take a single beam, this orange line. That's now red. The problem is a single beam is too narrow. If we were only updating cells along the beam, it would take a long time to build a map. So we might assume some thickness for the beam so that when it goes through some cells like this, we end up updating more cells as you see here. Now, to what extent you want to make it thick like this, it depends on the problem, and you don't want to go too far because then it will make it inaccurate because now you're updating the map based on assumption, not data. So there is a trade-off. Likewise, for the end part, when you observe the obstacle, you can think about it as a point, or you might assume, well, the obstacle has some sort of thickness, and maybe I am going to cover a little more area. And again, you don't want to do it too much because then you inflate the obstacle so much that it might not leave space for navigation. So in practice, you can expect to spend some time tuning these parameters. Although there are good initial values in a lot of open source libraries already. They tend to give reasonable results out of the box. So you might give them some names so we can implement an algorithm. So the thickness that we're going to consider for the beam is parameterized by this beta angle. We turn a single line to something like a cone. The alpha is this cylindrical thickness of the observed obstacle area. Now, in reality, this is a point. When we model it, this is an exaggerated version of how to model that point, that a single beam can cover a fair part of the map. This, if it's for, let's say, beam J, this is not the heading of the robot. So this will give you a range, D, and some bearing angle for that beam. So from a single return point, if this is my map, right? This. Now I can consider a range, this D, and an angle to a closest beam I have on the robot. So that will give me a range and bearing information. Now we want to know what to do with it. So if you look at the occupancy graph, it will be something like this. First is free. You might hit the obstacle. Then the probability for that orange region will be high, close to the probability of being occupied. For example, this is 0, this is 1. Maybe you consider anything from 0.35 to be free, anything below that, maybe anything above 0.65 is occupied, and then anything in between is just unknown. So then there will be a part that is beyond the obstacle. Potentially, your maximum range is bigger than this obstacle, but there's part of the map beyond that obstacle that is occluded. Because the occluded area is not observed, we won't update it. That's just a prior for some probability that is unknown. So this is another way to show this idea. Now let's put it in an algorithm.
On the last slide, is R the same as D from the slide before that?
Yeah, I think so. There's a... Are you talking about the algorithm that I just moved to?
The graph that you showed is R, and it says R over 2. Is that the same as D?
Where is R?
Right by the ZTN plus R over 2.
Oh, yes, I think so. We should. Fixed it. We're talking about this R. I think it's the first time I'm seeing it. Is that the same? I think it's alpha, it's not R. So this is talking about thickness around the occupied point.
I think Z in here represents whatever D.
Right. So Z is the, I have to fix this too. So let's leave D and no, Z is not D. We'll see why. So I'm just going to leave it like this. You have to go through the algorithm. Because D is what you predict. It's a predicted measurement. Z is what you actually observe. We're interested in their mismatch to detect if that's the cell that we should update or not. But this R, I think you're right. This should be alpha, right? Because we are assuming a certain thickness for the obstacle. Now, that is a problem because it's not like the obstacle is completely observed. If it's a table and you see the leg, maybe if the robot moves, you still hit the table. So there's a lot of room to make the map richer by maybe cameras and other information. But the basic idea is that I see an obstacle, I assume some thickness for it, regardless of what's going on in the real world. So the algorithm works like this. I want to ultimately return a log odd value at time t based on current knowledge of the robot pose and observations for the map cell I here. So what we're doing is that consider the center of mass of the cell to be xi and yi in line 2. Calculate the range and bearing relative to where the robot is located. That will give you r and phi. Now that you know the angle of the map cell in the robot frame, sensor frame, find the closest beam, because we might have multiple beams with fixed resolution are located on the sensor. Find the closest beam on the sensor to this particular cell. I'll talk about these two more. For now, we get the range and bearing of the cell in the sensor frame, in the robot frame. Using the bearing, we find the closest beam from a multi-beam sensor. If it's a single beam, of course, there's only one. This arg mean means that just loop over it, see which one is the smallest. Right? Because if the map cell in the sensor frame is located at, let's say, 30 degrees this side, and I have beams at like 25, 15, 0, 15, 25, then the closest one is the one that is at 25. There is no beam at 30 degrees. So we need to find a beam that is available on the sensor. Okay? So that's the closest beam. Now we work with the range. If the range R, that, nice change to R. This is the same thing as D. If the range R that we predicted for the cell with respect to the robot pose is bigger than minimum of the maximum range, and the distance you observe from the sensor, or the angle is bigger than that cone that we constructed. So this is saying that if the measurement is telling you something that is more than the maximum range, that's impossible, because there is a maximum range for the sensor to operate. This minimum ensures that you respect that physical constraint of the sensor. If it's not maximum, the minimum obviously will be the measurement plus half of that alpha thickness. So take the minimum to make sure you respect the physical constraints. Now, if the predicted range for the cell is more than that, that means the cell is not in your perceptual field. Or if the angle between the closest beam and the relative angle of the cell in the robot frame is bigger than that cone, half of that beta value for the cone, then it still is also not in the perceptual field of the closest beam to that cell. In that case, the cell should not be updated, and we should return the prior value. Else, if the returned z is less than the maximum range, and the difference between what we predicted for the cell and the actual measurement is less than half of that alpha thickness, that means we're dealing with an occupied case. Then we return a log odd that is for occupied. If this is also not true, and the range is less than predicted cell's range is less than measurement z, it must be free, because all the cells along the beam up to the obstacle are free. That's the negative information that we get from a rangefinder sensor. Negative because the positive information is that it's occupied. We don't directly get from sensor what's free, but we can easily infer that anything up to that point must be free, unless it's a glass for a laser. which is not that easy. Birds fly to the window. It is a problem in nature too. Don't blame robots. This is a harder problem than it looks. Now, your two question might be, where do you get these two? Well, I just mentioned that you might assume some thresholding probabilities and then use this 0.35, 0.65 to get the log odds. So L will be log of 1 minus 0.65, whatever it is. So you pick these thresholds, and then your inverse likelihood model is just throwing these fixed occupied and unoccupied log odds based on this logic. Now, this is just an idea, right? And it's been successful in practice. You can modify it in many ways. And people have done that. And for the robot, just quickly, so imagine you have this X, Y, and then you have a robot looking somewhere. And then you have a cell. The robot has this heading. And then you're going to predict a range. I need to. Then you're going to predict the range, R. And also, maybe an angle with respect to the horizontal axis. Now, this angle is arctangent 2 of delta y over delta x. Arctangent 2 because we want to get an angle between minus pi and pi. Delta x is the map coordinate along x direction minus the robot. These are robot position and heading. Similarly, delta y is yi minus y r. But we know that we should subtract the robot heading because we are actually after this delta here, right? We care about the relative angle of that cell. So hence, you see that phi is this arctangent 2 of delta y and delta x minus the robot heading to compensate the robot's orientation. Now, if that's not accurate, you can expect that you get all sort of drifts over time and inaccuracies. That's the importance of known and perfect knowledge of the pose to get a consistent map. So that's the initial calculations from line 2, 3 you see here. So now we did all of that. You have the algorithm now. You have the inverse tensor model. You can read the laser data, assuming you know the robot pose. Somehow. Although there is a way to run particle filter as you build the map, and that's called FastSlam, and it's known as G-mapping package that you see in ROS. That's what it's doing. It builds the map and runs the particle filter in the map as you build it. It works well. It's a very nice work, but it has a scalability problem because you can't use so many particles because each particle is tracking its own occupancy grid map. It's going to be very expensive if you use a lot of particles. But it is a very successful and useful package. So if you know the pose, you build from laser scans that you see here, we can build now this reconstruction of the environment as an occupancy map. This is an example of the 3rd floor of MIT C-Cell building. They move the robot. People do it here all the time as well. I just don't have an image. We have 3D map of this building from some of our research. And a lot of you have done this maybe in ROB 550. I don't know if you took the robot out, but you have done probably something like this. So you send a robot, and now you can map this. Now, if you have this map, you can actually later load this map and run a particle filter in it. That's what we talked about in the localization lecture. Your likelihood will be different, right? You do ray tracing to get a range, and then you have an actual range for each beam. You get the innovation, and then update the weights. So this covers the other side, which is the mapping part. Now, to summarize, this is, I would say this is the first method you should learn if you want to start looking into robot mapping problems, dense reconstruction. This is in the context of robotics. It's not in the context of computer graphics. You can make a lot of nice reconstructions, but you might need servers and offline calculations. These are algorithms that recursively we can run on the robot. So they've been very successful. If you have robot poses, it's relatively straightforward to implement this. And I do give you an example of that in the code folder. There's a mapping folder, and you have an example of it using Intel dataset. There's an Intel research office in Seattle. There's a dataset. The code is building a map using that. So cells are considered independent. Next time, we want to relax this assumption. First, we want to come up with a better way to perform the inference such that we get the variance for each cell, not just the probability. We also want to relax the independence assumption. This is an old idea to learn these probabilities, but there are a lot of research how to use machine learning also to boost these algorithms to perform better. What we will talk about is it is machine learning style of inference, but it's the kernel method version. It's not deep learning. Because it's a kernel method and it's straightforward to implement, it can be online. You don't need any offline training. That's what makes it attractive. To read about this, you can read chapter 6 for the rangefinder sensors, and chapter 9 is all about occupancy grid mapping in Probabilistic robotics book.